So after giving a brief overview of the algorithms that have been studied for the past 20 years, 30 years maybe already, I would like to focus now on the things that can be implemented on actual current devices. Okay, it's certain that quantum annealing is already a thing, can already be used for certain problems, but it is not what we expect for the future years. Okay, um, my work is mainly based on gate-based algorithms, so using quantum circuits, and that's the thing that I would like to bring up here because it is probably the type of algorithms that um, will be bring some quantum advantage sooner, and those are certainly the ones that will be implemented in the IGNITE project. Okay, so getting a bit deeper into those, I would like to say some words about quantum machine learning. Okay, as you may know, quantum machine learning is the intersection and interaction between quantum computing and machine learning. Okay, so this can be understood in both directions, this whole quantum machine learning thing, because it is true that, for example, some partners in IGNITE, for example, the ones working here in Delft, okay, use machine learning in order to work with the data coming out from quantum systems, okay, in order to be able to find patterns, to describe some system in a better way, okay, trying to get rid of useless information and so on. But the way we work or the way we use this word, quantum machine learning, is in the opposite direction, okay? We use quantum computing in the sense that we try to take advantage of quantum features, inherent features to quantum systems, okay, in order to find some advantage in machine learning algorithms, okay, either faster algorithms or more accurate algorithms, okay. That's what we do at Multiverse Computing, okay, and what I'm doing in my personal research, okay. So just as an introduction, we can have 4 different fields, okay, depending on the type of algorithm we are focusing on and the type of data we handle, okay. If it's classical or if it's quantum, okay, either of those. Some examples of them are, for example, in the case of classical algorithm and classical data neural networks, okay. In case of classical algorithm and quantum data, quantum state tomography, okay, the fact that you can extract a quantum state out of quantum circuit by means of performing some measurements in your device, okay, that is called quantum tomography. There are some algorithms behind that, but as a rough overview, that's it. In case of having classical data but quantum algorithms, we can have, for example, the quantum support vector machine that I'll introduce in just a few slides, okay? And in case of having a quantum algorithm and quantum data, for example, the matrix inversion or HHL algorithm, okay? Just for you to see it and have some taste of this quantum advantage, okay? You see some algorithms right on the left screen, the online perceptron, the least square fitting, okay, and so on. The speed up of these algorithms with respect to classical solvers performing the same task, okay. Those names in there on top of the table at the right are the names of the modules that are needed to perform such algorithms, okay. In case you want to explore some more about it, you can take a look at the references of the first slides, okay. But you can see what is important in this slide is that they are actually bringing some improvement to the scene, okay, in the form of speed up with respect to their classical content. Okay, that's the main thing to. So, for example, we have the HHL algorithm, okay, developed by Joyd and his team, where the problem is to solve a linear system of equations for n variables, okay, where you have to get rid of the matrix A in there, so you have to perform this inversion matrix and multiply it by B, okay? In terms of classical complexity, this scales as n, where n is again the number of variables in my system, while for quantum version of this problem, the scale is logarithm. Okay, so it's an exponential game in terms of complexity, which is quite useful when you have to tackle bigger problems. Okay, it's certain that true that you have some limitations in order to perform this algorithm, but the fact is that that you can really get some advantage out of it. Okay, for some specific problems, but it's in there. Okay, it's something really useful. Also, quantum principal component analysis. Okay, beating the counterpart, this classical principal PCA. Okay, where you have, for example, this correlation matrix. Okay, built out of data vectors, and you want to find the dominant eigenvalues and eigenvectors of such a matrix. Okay, if you want to perform that classically, you will have to go for n square, okay, complexity, while in terms of quantum algorithms, the scaling is logarithmic again. Okay, once again, we find an exponential advantage when implementing such algorithm. Okay, you can see that an example is where the data vector is stock prices, okay, between some or in some defined interval, and you want to perform principal components analysis, component analysis on that. Okay. One more, quantum support vector machine, where you want to classify a vector into one class or the other by means of hyperplanes, okay, separating the data that you are trying to handle and to classify. Okay, this again gives an advantage with respect to its classical counter. Okay, but still, those are far from being useful nowadays, because we would require fault-tolerant quantum computing, or at least a more powerful quantum circuit, okay, in terms of number of quantum gates you can introduce in your quantum hardware somehow, and well, correlations between qubits and depth of the circuit, okay? In other words, number of gates, okay? That is a limitation because of the lifetime of your qubits and so on, okay? Depending on the platform, you can get some let's say advantage, but it is still far from our reach. However, there is this new trend called variational quantum circuits. Okay, as I was introducing previously, it is the field in which I'm studying right now, that I'm exploring, and that we like a lot, Multiverse, because it gives a lot of let's say tools to tackle actual and current industrial problems. Okay, this is commonly a gate-based paradigm where you have your quantum circuit. Okay, you perform some measurements on it in order to extract information out of the circuit in the form of a wave function, in the form of a quantum state. Okay, you with that data, you analyze, or you, let's say that, try to find some certain characteristic or ground state of a Hamiltonian, for example. Okay, finding an optimal value by means of iterating the whole process. Okay, in the sense that you try to update your logical gate, okay, the parameters inside your logical gates, in order to get a quantum state that fulfills some certain function you are interested in. Okay, when I say fulfill, I mean allows you to go to the ground state, okay, of your cost function, Hamiltonian, whatever, okay? So that the quantum state going out from the quantum circuit is your optimal configuration, okay? For such a function, you have already implemented, okay? This is a whole iterative procedure where you have to introduce some classical software to be able to tackle the whole problem. Okay, this is a hybrid approach. So it is basically described in here by means of the variational theorem of quantum mechanics. You have certain Hamiltonian, okay, and you know for sure that applying it to a certain quantum state, you will get an energy that is higher than the ground state. So your goal will be getting as close as possible to that ground state by means of varying the parameters inside your quantum state. Okay, that's the straightforward way to get closer to an optimal state for your optimization problem. And there are a couple of variational quantum algorithms that are employed nowadays. Those are the quantum approximate optimization algorithm, okay, where you have to choose the depth of your circuit by means of choosing this M. It is a hyperparameter, okay, and then, as I was saying before, you will sample your quantum state out of the quantum circuit. Okay, you will introduce it into some cost function, and you will iterate the whole process of updating the parameters alpha and beta coming into the gates of your quantum circuit by an iterative procedure. Okay, something good is that this introduces the correct structure of entanglement of correlations in the variational circuit. Okay, in the sense that you can really access the whole Hilbert space of the problem you are aiming at. Okay, but things, well, that this quantum circuit might be difficult to be implemented in quantum hardware, because if you need many gates to perform such a task, you will not be able to do it using the quantum hardware we have nowadays. Okay. On the other side, we have variational quantum eigensolvers. Okay, this is similar to the QAOA. Okay, but in this case, we have the freedom to choose the circuit the way we want. Okay, therefore we can control the depth of the circuit, the quantum gate relating its qubit, okay, so that we can adapt the circuit to a certain quantum hardware. But on the opposite side, since we choose the circuit, okay, we don't know how the entanglement is getting inside the circuit. Okay, we don't really know if the structure of our ansat is correct. Okay, there are some current trends trying to explore this field by means of what is called geometric quantum machine learning. Okay, by trying to implement some symmetries in the circuit in order to access certain subspaces inside your Hilbert space and so on. But it's still something to be studied, okay? Because this is a trade-off between the freedom of configuring your quantum circuit the way you want and what you can really get out of the quantum circuit, okay, in such a way that it makes sense. Because maybe you can get a quantum state out of the quantum circuit. You can apply a certain Hamiltonian to the quantum state, okay, trying to look for the ground state of this Hamiltonian. But since you are not applying the correct correlations inside the system, you will not be able to access the whole Hilbert space, and you will not be then able to perform the optimization problem properly enough. Okay? So just for you to have a rough idea of what this variational quantum eigensolver is, we wrote some, in Multiverse, we wrote some papers devoted to this whole area of variational quantum algorithms. Okay, on the left corner downside, you can see that we develop a variational quantum algorithm to perform clustering, okay, and supervised clustering using only one qubit. Okay, you can go for more qubits, but in principle, you can classify, let's say, families, groups of points, by only using one qubit, okay, with no patterns in principle in your data set, okay, only limited by the fact that it will be difficult to convert to the good state, or you will not be able to separate data that is super close in terms of distances between points, because you will need to go for some semi-supervised algorithm and so on. But in terms of unsupervised algorithms, it works, and it's already something implementable in quantum hardware. Okay. Also, we have some examples of quantum optimization that varies in our quantum non-orthogonal optimization. Okay, taking advantage of the fact that a qubit can be divided into non-orthogonal states. Okay, using those non-orthogonal states as labels for performing some kind of optimization procedure, okay, in the sense that one label will correspond to a certain solution of your system, and you will be interested in moving your quantum state around until arriving to the label that maximizes or minimizes your Hamiltonian, okay? And the one that we wrote the latest, the variational quantum continuous optimization, okay, where we move step forward to try to work with gate-based quantum algorithms in a continuous manner, okay, in the sense that we can tackle problems depending on continuous variables, okay. This is kind of novel, and we think that this is an approach that could also be introduced for the Ignite project and industrial applications close to the things that we are planning to do here, okay? And just to finish it up, you can see that this consulting group called Gartner has distributed the quantum algorithms. You got an entire table depending on what the expectations are for their implementation in terms of time and the speed up that they will bring to the scene of, as I was commenting, machine learning and optimization problems. Okay, again, this is super useful, and in case you want to check it out, there are many references out there. In special, I would go for Nielsen's book in case you are not familiar with the topic, and I could be updated by means of arXiv for novelties in the field and news coming from scientists working on this area. Okay, so that's been all. Thank you all. In case you want to reach out to me and talk about the algorithms we are implementing in Multiverse, or something you would like to know about, we are very pleased to help you out. Okay.